So we left off the mobile number 8, page 353, I think it was. .354. And we calculated that mass 1 should be about 8.9 grams. At which point I was saying last class that we have to then combine these two masses here to be the mass that's hanging on this side. That's going to be 20.9. If this is 8.9 plus 12, if 20.9 is going to hang here, that'll allow us to solve for M2. And then we combine those two masses to have the one mass here hanging with M3, and we can solve for M3. So just kind of going backwards. And, the best way to solve this one. So getting back to this point here, mass 2, you have to get that. That's 2 centimeters. And 20.9 is 5 centimeters away from the axis of rotation. So remember, everything's with respect to where you're rotating it from, where you're spinning this object from. I can change it, I can have it anywhere. So I put it here, 1 centimeter versus 6, whatever. You're still going to have the same issue. M2 is still going to be the same thing in order to have balance. You're just changing your perspective, your origin, your axis of rotation. So continuing with that sort of thing, we gotta, then from the axis of rotation, we figure out the torques in the system and the direction of those torques. So if I was just looking at the torque provided by M2 or M2G, that torque would be in a counterclockwise fashion. And so that would cause the M2 would cause a positive torque, because using the right-hand rule, counterclockwise, so how do we know for sure that this is going to be a counterclockwise torque? We employ this method called the right-hand rule. And this rule only applies for 2 vectors that are going to be a cross product of each other to form a new vector. Like say a magnetic field is going to be the cross product between the speed of a particle and the magnetic field to produce a magnetic force. And that's going to also, of course, that's going to be a new vector that's going to be pointing in or out of the page. So that's another new vector that uses this right-hand rule logic. So pretty much all rotational vectors or vectors that are produced by rotations can use this rule. And there's the so-called left-hand rule, but this works the opposite. Anyway, bit of a tangent there. So right-hand rule. So let your fingers, the 4 fingers represent, you can do this in any way you want, but I like to have my fingers represent the actual force. And that's going to be my external force. That's going to cause the system to rotate. My palm, or the direction of the palm, is going to be that's going to be the radius or distance from the axis of rotation, the rotation point. And then your thumb is just going to represent, in this case, the direction of the torque. So if we we know that this is going to make a counterclockwise rotation here. If you can see my hand, that's going to look left hand. So you put your right hand up, you're going to have your thumb facing towards you, because your fingers are going to represent a counterclockwise motion, right? So it's going to be, this mass 2 represents a counterclockwise torque. Your fingers are going to be rotating counterclockwise, and naturally, the thumb is going to be pointing towards you, and that's going to be the direction of the torque. Now you might say to yourself, what about this palm with the radius? How do I know where the radius is going to be pointing? Well, in this particular case, what we want to do always is to configure the right-hand rule with respect to the axis of rotation, obviously. So the direction of the radius for mass 2 is going to be pointing towards the axis. So therefore my radius points inward here, and then my force is going to be, it's going to be pointing down, counterclockwise rotation, right? So if you do that, accurately, or the picture that we have here, my force provided by M2, my fingers will be pointing, in this case, will be pointing downward. We'll be pointing upward when we get to the other side of the rotation, but fingers pointing down. My palm is going to be pointing towards the right because that's going towards the axis of rotation. And then my thumb is still pointing out, and that's the direction of my torque, which is the positive direction. Out of the page generally represents positive torque, and into the page, negative torque. So now if we do the converse here for 20.9, 20.9 is here, pointing downward. My radius is going towards the axis of rotation here, pointing down. My thumb points in. That means that my torque pointing into the page will be a negative torque for a clockwise rotation. So that's just a little basics on the right-hand rule. And as necessary, we'll use it. But this is another way to visualize why things go clockwise or counterclockwise. So, okay, getting to the point of the problem, we have our net torque provided by mass 2, force of mass 2, or just the force due to gravity. Multiply that by the distance away from the axis of rotation. And then this is going to be subtracted from the torque provided by 20.9, or the 0.0209 kilograms. Multiply that by G, and then its distance of 0.05. Now the net torque is balanced, so it's going to be equal to 0. So in order to solve for M2, we set this guy on the other side and work it through quite easily. This was G's cancel out there. Or you can be glib like me and just keep them, and same difference. 0.0209 times 0.05. Divide that by 0.02, and that's going to be roughly 52 grams. So mass 2 is 52 grams. Using the same logic as before. And then going on to mass 3. (72.9) 4 centimeters. So M3 is 6 centimeters away. 72.9 is 4 centimeters. Right, 72.9 again. We solved for mass 2, which is 52, roughly 52, 52 and a half, whatever, that's trivial. So that's 72.9. That 72.9 is going to be this entire mass here. It's going to be the collection of all of that hanging right at that point. And so that's why we got that picture right there. It's the same difference. 72.9 counterclockwise torque, and then M3 has got clockwise torque. You can just set them equal to each other because you know that M3 is going to be a negative in the net torque equation equals 0. So put the negative on the other side, it becomes positive. So we have this. So M3G. And again, G's cancel. And you solve for M3. And that's roughly 48 or 48.6 grams for M3. So M1, like 8.9, M2, 52, and then M3, 48.6. So that's the continuation of number 8. So using balanced torques. So next what we want to do, and I'll let you do an example yourself, of course. We're going to go back to page 343 and take a look at the example of the man on the drawbridge. So we have a number of things happening here. This is kind of like your real life engineering balanced torque situation. You want to create a plank or the situation such that everything's in balance. Okay. And then this is okay, so we have plank that's rotate if left on its own. String here. So we have a guy standing roughly at this point. Okay, the length of the plank, 8 meters. So the weight of the builder, I guess. A uniform horizontal beam with a length of 8 meters and a weight of 200 newtons is attached to a wall by a pin connection. Its far end is supported by a cable that makes an angle of 53 degrees with the beam. A 600 Newton person stands 2 meters from the wall. Find the tension in the cable as well as the magnitude and direction of the force exerted by the wall on the beam. So there's a contact force by wall on beam. It's denoted as R. I guess you call it rotational force, or you just say whatever. It's the R force, the wall force. So the weight of the beam is 200 newtons. Again, that's going to be at the center of the beam itself, because the center of mass, the center of gravity, is going to be well at the center. Theta 53 degrees, or we idealize this beam as if all of the weight was collapsed at the center. So that's why it's at the center. Weight of the person, 600 newtons, and the person's distance away from the axis of rotation is 2 meters, right? So that's going to, imply torques. So let's go do this step by step. So step 1, we want to draw our free body diagrams on the system. So when we do balanced torque problems, it's always going to be forces and one torque equation, because now we're talking about things that are going to be rotating about some axis as opposed to just things that are static. Back in chapter 5, just draw your FBDs, but now we're going to be pivoting around some axis. Okay. Systems in balance. force is equal to 0, we know that the net force is made up of all the forces in the x and the y directions. So just drawing all the forces out. So this contact force from the wall and the beam directed at some angle, we call just R. And so therefore, this is going to be some arbitrary angle theta. It's not the same as 53 because, you know, this is not alternate interior angles there. So we have to figure out what that is in our journey. It's R sine theta, and this would be our cosine theta. So again, we're just dealing with the forces. The rear force directed at an angle. It's made up of two parts, cosine and sine part, as well as the tension, which we are familiar with. T sine theta and T cosine theta. The weight of the beam is, you know, concentrated at the center. And the weight of the person is 600 newtons pointing down. So step 2, get the Fx, Fy, and torque equations. So all the forces in the x direction, again, because, right, our perspective is x, y like that. Very simple orientation. So if we were looking at all the force x, we have r cosine theta minus t cosine 53. Everything's balanced, equals 0. So again, t cosine theta, you know, theta for t is 53. So that's going to be negative direction, r cosine positive, all those in the x direction. And then y, we have one here, one there, and another 600 and a 200. So r sine theta plus t sine 53, 600 and 200, so 800 down. That all equals 0. Like I said, it's going to be one torque equation, whether it's balanced torques or unbalanced torques. It's going to be one torque equation that's going to either add up to 0 or it's going to add up to a form of mass times acceleration, which we're going to see later on that the net torque equation for unbalanced torques, when the system is actually rotating with an angular acceleration, is going to be torque equals moment of inertia times angular acceleration, I alpha, which is very similar in concept to F equals ma. So all the torques in this case is going to be the torque by the rear force. Let's just, you know, do them systematically. The torque provided by the person, the torque provided by the beam, the torque provided by the string tension there. And we know that's all going to be equal to 0. We know that there's no torque provided by the rotation force because it's right at the axis of rotation. There's no torque here because torque implies force and a distance. Well, there's a force, but no distance, so TR goes away, right? And so we just have the torque provided by the person, the beam, and the string at the end, because those all have distances away from the axis of rotation. Find the axis of rotation. What's the force at that? What are the forces? What are the forces in the system? What are their distances? they have distances, they have torques. Person has a torque, beam, and string. And now, after we establish that, what's the direction of those torques? We look at them individually. If we were looking at the torque of the person, and this is the axis of rotation, ignoring everything else, the system would move in a clockwise fashion. Does everybody see that? Any questions about that? Ignoring all these other forces, just looking at 600, the beam would rotate. Here's the axis. It would rotate clockwise. And same with the beam itself. It would provide a clockwise torque. The string would provide a counterclockwise torque. The T sine component, because it's the component of the force that's perpendicular to the distance that provides the torque. So this left on its own would make a counterclockwise. Positive torque, negative, and negative. None. And we're done. So that becomes negative 600 newtons times this distance, which is 2 meters away. That's the torque provided by the person, and the torque provided by the beam, and then the torque provided by the string, T sine 53. Multiply that by 8 because he's at the very end. So we can get the tension right away, and we need to get the magnitude of the force of the wall on the beam. That's going to be next. So that's pretty simple. I hope you see that. T sine 53, 8. So we know that this is going to be 1200, 800 on the other side, because it's going to be, so that's 2000. Okay, so I'm going to go to the next slide, so make sure you get that. Ran out of room there. So easy, solve for T. And you can see it there in your example, but I'm just probably putting a couple other nuggets in there. So it's going to be 2000 newtons. And that's going to be, when you solve that out, divided by 8, 8 sine 53. It'll be 2000. So the tension is 313.5 newtons. I think that was perhaps pretty easy for you. Questions? So now what? In order to get the R force, step 3, one thing we can do is use equation 1 to find an expression for R cosine theta, or you can use equation 2 to find an equation to get an expression for R sine theta. In either case, you want to get something, because you have two unknowns. You have R cosine, you have R sine. Get an expression for one, substitute back into the one you didn't, right? Logic is your systems of equations that you see in algebra. You just now have to expand your viewpoint. sine theta. All right, so let's use equation 1. Remember that was our cosine theta. So we have our cosine theta itself is 188.36 newtons. So now, step 4, next step here. Let's get an expression for r sine theta, because now the point of that, as you can see, an example is to get the angle of get the ratio of r sine over r cosine. That allows you to get the angle of the force r, and then you can solve for r, which is the ultimate goal. Step 4. Again, this is minus 800 because 600 and 200. So again, that's 800 minus t sine 53. We know what t is. (800 minus 250) gives me 550 newtons. Now the ratio, r sine over r cosine, which is basically tangent because the r's cancel out there. 550 over 188.36. That's 2.92. So basically, tangent of theta, the r theta, is 2.92. So we get the direction of r, magnitude and direction, and then it's very easy to get r. So r cosine theta, for example, we already found the expression for that, 188.36, or use r sine, same difference. And then r is over cosine of, that's 580 newtons. And so that's how you approach that. First of all, and I just follow the steps. This is really kind of the main logic of these realistic balanced torque problems. Steps 1 through 4. Get your FBDs. Put your FX and FY equations, which you're familiar with, and a torque equation. Step 3. Step 3 and 4 are like substitutions. You won't always have to do a substitution, but those first 2 steps are crucial. Oh, of course. Just let me know when.
A little bit down. Yeah, right there.
So yeah, steps 1 and 2 are vital, and then everything else is like, okay, what is the problem telling me? Okay, I have 2 expressions that are unknown. I have my r, I don't know my other theta, so I have to do something. Okay, so let's get to yes, of course. It will be up. So let's take the same problem. Okay, this is all of it's going to be similar to skills test, but this one's more relevant. First one is the logic, and now let's apply it. What if I had my beam like this, and then now, let's say my tension at some angle there, let's say the angle is reduced to 35. Everything else is equal. Person still standing 2 meters away. What would be the tension and the R force in this case? So you can just practice that for the rest of the time. So the only thing I changed was orientation. The angle is now 35. Go for it. As far as the style of skills test, it's going to be similar to this style. Okay.